All right, I think we can get started. Good afternoon, everybody. Welcome to the ASTRA-sim and Chakra tutorial at Micro. So my name is Tushar Krishna, and let me go ahead and get started by introducing the organizers and presenters. So I'm Tushar, I'm a faculty member at Georgia Tech. With me is William Vaughan, who's a PhD candidate at Georgia Tech. He's also on an internship at AMD. Jungan Park, who's a postdoctoral researcher at Georgia Tech. Taekyung Hyo, he's a senior HPC middleware developer at NVIDIA. And Vinay Ramakrishna, who is a senior member of technical staff at AMD. And we'll also have Ruchi Shah from AMD, who will also be contributing to the tutorial. So this effort is actually something that's taken several years with several contributors, and some of their names are listed. I think some of the folks from Georgia Tech who've been maintaining the code base, some of the core people from Meta who have been involved both in Chakra as well as ASTRA-sim, folks at NVIDIA, Intel, AMD, and several other companies. So it didn't have space to list folks, and also a lot of this work is being done in collaboration with the Chakra working group at ML Commons, and several people who are members there have also contributed to this entire effort. So this is the overall agenda of what we'll be talking about today. So I'm going to kick things off just by giving you an overview of distributed ML, just to kind of set the broad context and briefly introduce like Chakra and ASTRA-sim at a high level. Then Taekyung will come and talk about the Chakra execution trace itself, like talking about the trace format, how to collect it and so on, and go on to the ASTRA-sim workload layer. Then William will talk about the ASTRA-sim system layer and network layer. Then we'll have the coffee break. After the coffee break, we have more of a deeper dive. So Jungan will actually do a demo of Chakra and ASTRA-sim with some interesting case studies. Then we'll talk about some new features that have been added. Vinay will be leading that. Then we'll talk about some of the efforts around just the maintenance of the wiki and the validation, just to kind of tell you where you can find more information. And finally, we'll conclude. So that's the broad agenda. So we are recording the tutorial. We do plan to post it later as well. So just something I wanted everybody to know. This is the web page where all of the material from the tutorial will be uploaded after the tutorial, both the slides as well as the video. Okay, so with that, let's get started. So again, you are in this room because you kind of know this, like AI has become a distributed system problem. If you look at, stats from GPT-4, it was trained on over 25,000 GPUs, and even inference for some of these models is run over tens of hundreds of these GPUs today. And the reason for this is, several trends that have come together. One is large ML models. Of course, we've seen versions of charts like this, models that are scaling at an unprecedented rate. Moore's law has stagnated, so we can't simply rely on device scaling. So compute performance is only going up at about 1.3x per year. Memory capacity and bandwidth also at about 1.2x per year, right? There's large training data sets, especially for many of these frontier models that demand a lot of memory capacity, as well as correspondingly lead to high amounts of compute. And on the inference side, there's a lot of diverse inference use cases, which have diverse requirements in terms of, the sequence lengths, the context sizes, and how that affects, the overall performance in terms of time to the first token or the overall latency. So with that, I think in terms of the system, there have been several implications. So multiple devices are now required to accommodate large-scale machine learning, right? So as an example, like GPT-4 required 21 yottaflops. And a single, NVIDIA H100 like GPU would end up requiring like 333 years to train a model like this. On the memory side, like GPT-4 is rumored to have about 1.8 trillion parameters. So just to store the model, you would need about 3.6 terabytes. And just to store the model, you would need like 45 GPUs, right? And this is not even counting the additional GPUs for throughput or additional memory for intermediate states. So this has, of course, led to several AI platforms or AI supercomputers that people have been building. So almost all of the major vendors out there, Intel, AMD, NVIDIA have solutions. A lot of cloud providers have their solutions. And there's, of course, a bunch of startups that are all in this space trying to build these large platforms. So from a 100-foot view, this is kind of what many of these AI platforms look like. You essentially have these NPUs at the endpoint. So in the interest of generality, we'll keep using the word NPU for neural processing unit, Today, for the most part, these are GPUs, but these could be, ASICs as well. And then you have these custom fabrics to connect up these NPUs, both to scale up and then to scale out. And so with all of this, let's now, I think my purpose will be to just kind of give you a quick, background 101 on how you actually execute models on such platforms, right? So at the core, you have a model, you have data, and if you kind of, squint, almost all of machine learning neural networks are just matrix multiplications. And so what you do is you're essentially, multiplying these to get the result. And if you just do the forward pass, that's inference. And if you use the result, calculate a loss against some ground truth and you update the model, that's training, right? That's the kind of the high level view here. So what happens if you have a distributed machine learning setup, the one that I was talking about? You would either, shard the model itself because you cannot fit it across the memories of these NPUs, or you would shard the data samples. And again, like both of these are done, and we'll talk a little bit about like the pros and cons. And so ultimately, as soon as you have a distributed system, communication becomes something that you need to care about. You need to synchronize data. So as an example, if you're, sharding across the NPUs here, they'll generate partial results that need to be exchanged with each other to get the full result. So some of the systems challenges with distributed training are fundamentally around communication, right? That's inevitable in any distributed algorithm. And the communication really depends on several factors: the synchronization scheme, the parallelism approach. And one question we, want to answer is that really a problem, right? And so the answer is it really depends. It depends on whether you can hide the communication behind the compute. If you can hide the communication behind the compute and you're utilizing all of your expensive flops for, just do the computation, that's great. But if you cannot, then it starts becoming a problem. So how do we determine this, right? And the challenge is that the hardware software co-design space for distributed machine learning is very, very large and intertwined. So we've tried to, kind of understand this, and I've tried to, showcase this with 5 colors. So the green part is, really what's called as the workload layer in our terminology. This captures the model characteristics. So think of things that you're trying to define in, like, let's say, a framework like PyTorch, right? So that is basically what the green color is trying to capture. Then, we have this, we have like the light blue and dark blue to represent the compute and memory components over which, you're running these. The pink part is what we call as the system layer. This is meant to capture the system software that is used to orchestrate a lot of the communication. So collective communication libraries would essentially come into this layer. And then you have the orange part, which is what we call as the network layer, which again has both like a software component and a hardware component to ultimately navigate all of this, right? So let's go kind of step by step through each of these just to understand what each of these contain. So when we talk about DNN models, this is really the specific model that you would like to train or serve, right? Then the workload parallelization strategy, as I said, is, how do you actually take the model and shard it? Then you come down to the communication policy and patterns where, do you do it as a centralized parameter server or do you do it in a purely distributed manner? And then some framework level scheduling around, synchronous, asynchronous, or blocking versus non-blocking. Then you go down to the compute and memory. This is where, as I said, like what is the exact, GPU, let's say, that you're using, how many flops, what is the microarchitecture, what's the memory bandwidth, capacity, all of those kind of come into these decisions or these components. As I mentioned, the system layer is where you have a lot of the collective communication support, the libraries, both the collective algorithms as well as the low-level scheduling. And finally, on the network side, transport layer, you might be using RDMA or TCP or, GPU direct RDMA and so on. How do you actually design the endpoints, the number of links, bandwidth per link, the architecture, whether, you have maybe an on-package solution and so on, or whether you're doing off-roads to the NIC, compressing and so on. And then down to the actual fabric design and topology. So do you have like what kind of topologies do we build? Whether it's a torus, whether it's switch-based, do you have a flat topology, hierarchical, all of these decisions down to like, low-level hardware around like microarchitectural things like the buffering strategy, flow control, arbitration, how do you do congestion management, and so one, of course, big challenge here is this, tussle between, navigating co-design and abstractions, right? So these abstractions are great, but we would also like to co-design across the stack for efficiency. And so we want to understand each of these so that we can actually take judicious and efficient decisions, right? That's the goal. So with that, let me kind of go over each of these components one by one. So on the DNN model side, this is really just the model architecture that you're describing, as I said, in a PyTorch or a TensorFlow. You might have like, convolutional neural networks, you might have like transformers, you might have recommendation models. And of course, from a computation or, system perspective, it boils down to a lot of the different kinds of operators that you're running and their dependencies. So whether it's conv operators, matmals, attentions, fully connected operators, and so on. And as we said, like the parameter sizes can be from millions to trillions here. So moving down the stack, like the workload parallelization strategy is where we decide, how do we actually parallelize the entire model or data. And there are several different ways of doing this. You could either split across the mini batch, which is called data parallel, or you could split the model itself, and you could either split across the tensors, and it's called tensor parallel, or shard across the layers. This is called pipeline parallel. And then, of course, this also defines what the actual communication pattern will be between the different nodes. So as an example, like this is what data parallel does. So data parallel essentially distributes, the data or shards the data across multiple nodes and replicates the model. So of course, here the assumption is that, the model is kind of can actually fit in the memory of each of these NPUs. And so in data parallel, as I said, what you would do is you would shard this, split it across the memories. And now from a communication perspective, like each of these NPUs has a full copy of the model. They're just running, the forward pass on a subset of the data samples. And so there's just the inference communication or the inference compute on the forward pass. There's no communication. On the backward pass, though, for data parallel, since you have only partial data samples, you're only computing partial gradients, so you have to actually communicate. So what ends up happening is you have to communicate the weight gradients. This is typically done via what's called an all-reduced collective. I'll talk about that a little bit later. This can be done in a non-blocking manner because you can go ahead and start computing the input and weight gradients while the weight gradients are being communicated for synchronization. And at the very end, you need to kind of wait for all of these to finish before you can start the next training iteration. So there's one blocking step here. Another parallelism strategy is what's called tensor parallel. So tensor parallel is where you actually shard the model itself and try to distribute model weights across different NPUs. And so in this example, I've kind of split this across these two NPUs. And give me 1 second. Yeah. And now in the forward pass, what's going to happen is now each of these NPUs only has parts of the model and they don't have the full model. So they are only computing partial activations. So even during the forward pass, they need to communicate. And because each layer needs like the full, full activations from the previous layer, this communication is actually blocking. So during the forward pass, you're doing the compute for inference, doing a blocking communication, inference, compute, blocking communication, and so on. And then during the backward pass, you're communicating the input gradients, and this is again done in a blocking manner. At a very high level, you can already see that tensor parallel ends up having a more rigorous communication pattern, and that's kind of the cost because the model just couldn't fit, and you don't have a full copy of the model. Another parallelism strategy is what's called pipeline parallel. So this is a subset of model parallel. Again, you're still splitting the model, but here you're trying to kind of split the different layers and have different NPUs work on different layers and just operate in a pipeline manner. So here the communication pattern basically involves, again, you're doing the first layer, let's say on NPU1, then you have to communicate the gradient out activations with NPU2. This is again a blocking step. NPU2 can't start till it actually receives these. Then it does the computation, passes on the gradients and so on. And in the reverse, again, you have like the same, input and weight gradients getting communicated, and the communication is blocking, but now just neighbor to neighbor, right? Or whatever, GPU to GPU instead of across mainland. So pipeline parallelism has these challenges in terms of, filling up the pipeline and draining it as most pipeline solutions do. So you have issues related to bubbles. And typically what you do is you decompose mini batches into micro batches and propagate them so that you can get, better utilization. So again, so this is a very active area of research, in terms of identifying the right parallelism strategy. And there's also a lot of sophisticated schemes that exist out there. Pipe Dream from Microsoft, Megatron from NVIDIA, Zero from Microsoft to also handle optimizer state, FSTP or fully sharded data parallel from Meta, and so on. I mean, you can certainly take a look at these to understand more on different parallelism strategies. But basically, it boils down to these parallelism strategies and the specific communication patterns they lead to. So now this gets to communication. So on the communication side, broadly, there are, we can kind of classify them into the synchronization scheme and how the communication is handled. So the synchronization itself could either be, synchronous or asynchronous training, right? So synchronous training says that we kind of wait for, all the NPUs to get done for this training iteration before we move to the next training iteration. Asynchronous kind of has the intuition that anyway we're propagating errors, and like the system might be robust enough that we can actually have certain NPUs work on stale gradients and so on. So again, this is an interesting question by itself, but typically synchronous training is used quite actively in practice, and that's what we actually support in the simulation infrastructure. Communication handling is about, okay, so we have to do some communication. I showed you different patterns, like, different NPUs that need to communicate. How do you do this? Do you have some central server that handles all the communication? That's called a parameter server, in which case each node would send its model gradients to the parameter server for it to kind of get reduced with the other gradients. So you always have the up-to-date copy of the model sitting at the server, and this then kind of, redistributes it back to the different NPUs. Again, just like any central scheme, this has trade-offs with, a central entity might becoming a bottleneck and so on. A more, something that's used a lot more in practice today is a purely peer-to-peer distributed scheme, which uses collectives. So the idea is that compute nodes can directly talk to each other to globally reduce the gradients and update the model through different collective patterns like an all reduce. And these collective patterns kind of, come from MPI, and I'll talk about this also in a bit. So ultimately, as I said, exchanging output activations or input gradients depends on the parallelization strategy, and also whether or not we support collectives or use direct node-to-node sends receives. So this is just a table kind of summarizing the high level, what kind of communication needs to happen if you have parameter server or collective based, depending on the parallelism strategy. So now moving on to, so we've talked about the workload layer. Now let's talk a little bit about the compute and memory layer. So here, just the main thing to remember is, okay, let's try to understand what the compute itself is. I'd already alluded to this. Fundamentally, you are performing a matrix multiplication. So forward pass, you're just multiplying the inputs with the weights and getting the outputs. And in the backward pass, you are computing the weight gradients by multiplying the input activations with the input gradients. And then you're computing the input gradients for the layer I by multiplying the input gradient of layer I plus 1 with the model weight. Right? And so this is basically used for then updating the model parameters. And these are also just matrix multiplications. Now, fundamentally here, that's where there's a lot of hardware out there that really optimizes for running matrix multiplications. Again, as I said, GPUs are one of the most pervasive today, but almost, I mean, there's a lot of ASICs out there, and even CPUs today have support for running matrix multiplications. Ultimately, compute efficiency depends a lot on the amount of data reuse you can get. So on the compute side, fundamentally, you are trying to extract data reuse because, if you have any matrix vector multiplication, that vector is reused across, many rows of the matrix. So one way of understanding this often is to use roofline plots, where you can see, if my accelerator or my NPU has a certain, peak flops that it can provide, depending on the number of, let's say, MAC units it has, and there's a certain memory bandwidth that is provided, then you can divide, this into two regions, the compute bound and the memory bound region. So the compute bound region just says that your ultimate throughput is going to be bound by the number of compute units. So all the units are utilized, and the maximum performance you can get just depends on the maximum compute flops you have. While if your performance falls in the memory bound region, it means that your limit is the memory bandwidth. Like you can't actually get higher, better utilization because you're just waiting for data. So typically, the more data reuse you have, you tend to be on the compute bound region, otherwise in the memory bound region. And for a lot of models, so convolutional neural networks typically fall in the compute bound region, but transformers that are part of LLMs are known to be heavily memory bound and fall within this region. So again, kind of the main takeaway here being that on the compute and memory side, memory bandwidth today is a very, very precious resource because a lot of models are not able to utilize all of the compute and fall here. And what is the implication of that? Like, I think the implication of that ultimately comes to, communication, right? So if you are, if your compute is actually very efficient and you can utilize your compute more better and better, then your communication can start becoming a bottleneck. So in this chart, I'm just trying to show that, as your compute power becomes better and better, your communication time starts becoming exposed. So this is a term that we also will use throughout the tutorial. So exposed communication is all the communication that you could not hide behind the compute. As I mentioned earlier, ultimately the goal is to try to hide all the communication behind the compute. All right, so now we move on to communication, right? So communication is something that we need to manage. As I said, the more efficient the compute is, it might be something that's exposed. So here, again, as I mentioned, like the reason for communication is simply the fact that we are sharding either the data samples or the model weights, and ultimately we need to synchronize. And so as an example, if I'm doing tensor parallel that I showed you earlier, both the NPUs are generating partial results. And as I mentioned earlier, you have to do some form of synchronization to get the final output. And that's basically what leads to communication here. So as an example, suppose I have like 3 NPUs here. They have these partial, activate. They have all generated these activations. The synchronization step would essentially have all of them communicating these activations to each other so that they have a full copy of the model. And this particular pattern here is what's called an all gather, where they're just kind of gathering the data. So this gets to the notion of collective communication patterns. So these are the ones that are most pervasive in distributed machine learning. So given a specific parallelization strategy that I had mentioned earlier, like data parallel, tensor parallel, some hybrid, FSTP, 0, and so on, you may have one or more of these patterns show up. And these patterns are things like reduce scatter, all gather, all reduce, and all to all. These are the most popular ones. So reduce scatter basically just tries to, as the name suggests, it tries to do a reduction and then scatter the outputs. And all gather, as I showed earlier, is basically just a broadcast. And all reduce is really a reduce scatter plus an all gather. So you do a reduction, scatter the outputs, and then gather them. So this is basically what would be done if you're computing, let's say, partial gradients, and all the GPUs then have to communicate and synchronize, add up the gradients, and then distribute it all back, because ultimately for the next training iteration, you need a full copy of the model. All to all is a pattern where, like, I mean, as it's shown here, all NPUs are just sending data to all other NPUs. This is something that shows up a lot in a mixture of experts models and so on. So given a collective communication pattern, so the pattern is just more of a mathematical formulation. Another term you'll see in literature is collective communication primitive. So this is just a mathematical formulation that this is what needs to happen, based on the data that's there at the different NPUs. But an algorithm is how this actually gets executed and implemented in your system. And so I like to think of this almost like a routing algorithm to implement your collective patterns. And so there exist collective communication libraries or CCLs, most popular ones being, Nickel from NVIDIA, there's RICL from AMD, one CCL. There's also libraries like Microsoft's MSICL that basically have diverse collective communication algorithms implemented for these patterns, right? So we often think of these as more like textbook, algorithms, ring, direct, halving, doubling, and so on. And I'll give some examples. And so the interesting thing is, given a specific network topology, an efficient algorithm exists to run that collective pattern. And that's called a topology-aware collective algorithm. So as an example, suppose I have 3 physical topologies here, a ring, a switch, and fully connected. This is what a ring all-reduce collective algorithm would do. So this wants to implement the all-reduce pattern. And the algorithm basically does the following. I take my message and break it into 4 chunks. In this example, there's 4 GPUs, so I break it into 4 chunks. And the goal is that every GPU or every NPU takes one of the chunks and it forwards it to the neighbor, meanwhile receiving the chunk from its neighbor and adds it up locally. So in this example, 1 was able to send chunk number 4 to 2, 2 sent chunk number 1 to 3, 3 sent chunk number 2 to 4, and so on. And then they added up that value locally. So the color becoming darker is just trying to show that there's reduction happening. And you kind of keep doing this step by step. And so in 3 steps, you've sent these partial gradients to your neighbors and you've added them up. And what has now finished is the reduce scatter step. So at this point, we've actually mathematically done exactly this. The partial values have been added up and the values have been scattered. And then I do what's called an all gather, where I would just take a copy and just like take a copy, send it to my neighbor, hold on to a copy, send it to my neighbor, and so on. Right? So I basically do this kind of a broadcast. And again, at the end of 3 times steps, and all gather has also finished. And so the all reduce has finished. So this is actually great. So this collective algorithm used all the links. So in this case, in every time step, all the links of this ring were utilized and there was no congestion. So this is why this is a very optimal topology aware algorithm for this topology. Of course, in principle, you can run, like different algorithms and different topologies. So let's move on to a different algorithm. Let's say a direct all reduce. In this case, I have a different topology. This is a fully connected topology. And now in this case, instead of running a ring, I could still run a ring, but it would not utilize some of the intermediate links, right? I can do what's called a direct or a one-shot all reduce, where in one stop, I just send my gradients to all of my neighbors. They add it up. The reduce scatter is finished. And in the next time step, I finish the all gather. So again, this is, all links are utilized, no congestion. And another algorithm that's popular for switch-based topologies called recursive halving doubling. So this is known to be an optimal algorithm for switch-based topologies, where you kind of do this exchange in a pairwise manner. So 1 and 2 kind of exchange gradients, and 3 and 4 exchange gradients, add them up locally, then 1 exchanges with 3, 1 with 4, and so on. And so at the end, you've exchanged your gradients with all the other GPUs in a pairwise manner, and you have finished the reduced scatter. And now, again, you just, again, in a pairwise manner, copy the data from each other and do this broadcast, and then all gather has finished. So again, all links utilize no congestion, right? So these are basic collective algorithms. So almost all the collective libraries I mentioned implement these. But what about other topologies? There are other topologies out there. Let's say you have a torus, a simple ring algorithm would in principle work functionally, but it would lead to underutilization. So there exists other more sophisticated collective algorithms. These are often called multi-phase or, multi-rail or hierarchical algorithms, where you try to kind of do this in phases. So let's say I have let's say a three-dimensional topology here. I do a reduced scatter in the first dimension, followed by a reduced scatter in the second, followed by a reduced scatter in the third dimension. So again, on a torus, you would do it on one of the rings, followed by the next, followed by the next, and then kind of do an all gather in reverse. So that way you would again end up utilizing all of the links and get back the topology awareness. So this is kind of what a lot of the collective communication algorithms try to do. And so this is the system layer. Then kind of moving down, so this is all software, right? So now moving down to the network layer, as I mentioned, there are, decisions at the transport at the endpoint level that I won't go into in the interest of time, but let me give you a glimpse of the kinds of decisions you take at the fabric design and topology level. Here is where you're trying to build different network topologies. So let's say you have, a plethora of technology options, like you have like chiplets and advanced packaging and wafer scale to build, to scale up to a certain point. Then you want to use rack scale interconnects like NVLink or XC-Link or XGMI. And then you have like InfiniBand or Ethernet or even optics, right? So you can kind of scale and build these larger systems in this manner and kind of end up with like hierarchical network architectures like that is shown here, where you have, kind of the network architecture on package, followed by like intranode, followed by scale out across the data center. So examples of this are, again, like several systems out there, right? That we would like to, I mean, the goal of this entire tutorial is to try to model and study systems like this. So in fact, several different examples of systems out there are using, different kinds of solutions for scale up and scale out. So in this case, some of the ones on the left have, these electrical interconnects that are used. Some of them have custom intranode followed by internode solutions. Some of them try to use things like Rocky for RDMA over converged Ethernet. There's also solutions out there that are trying to use, as I said, photonics or on package meshes, wafer scale, and so on. So this is another kind of phenomenon that is prevalent in most of these AI platforms today. And finally, moving down to the network implementation, this is where you can think about implementation of the buffering, the flow control, arbitration, congestion management, and so on, right? So you might, for example, be curious about comparing, say, and for a scale out system, let's say InfiniBand versus Rocky, right? And so, how would these compare in terms of the delays, the congestion control mechanism, configurations, and so on. So these are the kinds of decisions that can be taken at that granularity. All right, so just to kind of summarize and have the takeaways for this part of the tutorial. So the design of distributed AI/ML platforms is an ongoing and open research area. There are many emerging supercomputing systems being specifically designed for this problem, and co-design of the algorithm and system offers high opportunities for speed up and efficiency.